my great pleasure to welcome Jason Hartline back to the department. Jason got his PhD here about 9 years ago, and I had the good fortune of being his advisor. And he's gone on to an illustrious career in algorithmic game theory. He's one of the young superstars in that field. So it's a pleasure to have you.
Thank you. OK, I want to start by sharing with you an email that I got not too long ago. And this is kind of a standard email that I might receive, because I give talks occasionally at places. And it wants the usual things like a title, an abstract, a bio, whatever, and a talk-related graphic. And I do a lot of math and computer science theory, and I don't really draw a whole lot. So this was the most problematic talk abstract request I've ever received. But fortunately, there's the internet, right? And in particular, this is a Chinese-based crowdsourcing website which specializes in graphic design. And so what you can do on a website like this, if you speak Chinese at least, is post a description of a task and a monetary reward. For instance, you could say, I need you to design me a graphic that depicts, well, this was in particular for this talk that I needed the graphic. So I needed a graphic that depicted crowdsourcing. And a reward, for instance, $120. And then you wait a week. And then you get a bunch of graphics to look at, and you choose which one you like the best, and you pay them $120. And so I did that. I crowdsourced the graphic for this talk. And I got a bunch of kind of interesting submissions. And so here are some of them. Some of them look kind of like flowcharts, which weren't all so exciting. More flowcharts. And some of them were a little abstract, and I didn't really understand what they meant. This is the web of crowdsourcing, apparently. And some of them, even I could have done better than. This one was pretty good. So you probably want to see which one I chose as the winner. And in fact, this one was the one I thought was the best. And so this flyer got posted all over campus. And this is the first time I ever had a pretty graphic posted on a flyer for a talk that I was giving. First and last time I had a pretty picture on a flyer. So what's the motivating motivation for this work? And one of the things that you might have noticed automatically is that, well, I posted this task and this reward, right? And I got a bunch of submissions. In fact, I got 18 submissions. And I chose one to go on the flyer. So the submissions of 17 people were just wasted, right? So is this a problem? And so some things you might wonder about crowdsourcing is, well, you want to sort of know, is it an efficient means of procuring services, right? So, about this wasted work, can I show that we're not wasting too much work? Because that'd be pretty disappointing if I, wasted just tons of people's work to get this one graphic, and 18 people made graphics, right? And I might want to compare crowdsourcing as a means of procurement to some other more standard means of procurement. Like I could have maybe tried to hire someone. I could have posted an ad on Craigslist to try to hire a graphic designer to come and design me a graphic, right? And so I might want to compare crowdsourcing to those more conventional methods. And then, maybe if I'm going to find I'm going to do crowdsourcing on the internet, right? Well, what's the best set of rules for a crowdsourcing contest? We talked about one where I post a reward and I solicit contributions, and then the winner, the one with the best contribution, gets the entire reward. But there are a number of other options you might have here. Like, for instance, you could give the winner 2/3 of the prize, and the second best one 1/3 of the prize. Or you could dynamically decide how much the reward gets distributed amongst all the participants as a function of how good they are. Was there a question?
Yeah, on test CN, are you required to pick a winner?
So the question was, on task CN, are you required to pick a winner? In most of these crowdsourcing sites, you are required to pick a winner as long as someone meets some minimum criteria that you had in your description. Okay, so if you say nothing meets the criteria, then you don't have to pick a winner. I don't know much about the conflict resolution they do in case something goes awry in this process, like you don't pick a winner, but there was a good one. I don't know anything about that. Okay, so those are my motivating questions. And what I'm going to do is I'm going to use auction theory to answer these questions. And so auction theory studies economic scenarios where you have scarce resources and many participants competing for these scarce resources. So auction theory is relevant really broadly. And in particular, it's relevant for this setting where my scarce resource is the $120 I'm giving out, and people are competing for that $120 by submitting these graphics that they drew. Okay? But I want to point out that even if you don't care very much about crowdsourcing, if you care about distributed systems or the internet working well, you care about what happens when people compete for strategically for scarce resources. Because any economic system, and the internet is one, has this situation where there are lots of selfish people who are competing for the network resources. And when you want to download your movies over Netflix, right, you want them to download fast. And so you're going to potentially try to strategize and game the system to get your resources, to get more resources for yourself. Okay, so let's start our discussion of auction theory. And this is basically a couple Nobel Prizes in economics that I'm going to be talking about. So this is really foundational, excellent theory that we're going to be going over. And let's start with the simplest example you could come up with for understanding scarce resources with strategic agents. So I have one resource, we'll call it an item, and I have a bunch of bidders who have private values for receiving this item. And the bidders have their own objective in mind. They want to maximize their value for the resource minus the price they have to pay if I charge them. Okay? And we're going to be trying to design an auction which is going to solicit bids, it's going to choose a winner, and it's going to assign payments. Okay? And I'd like to design an auction to maximize the two classic objectives in auction theory. One is social surplus, which means you want to give the resource to the player who can use the resource the best. Okay? And the other classic objective in auction theory is to maximize the seller profit. You want to assign the resource, actually you don't care to whom, but you want to maximize the payments you receive back for the resource. Okay, so these are the two standard objectives you might look at in auction theory. So let's look at a couple auctions. And so the first auction you might think of is just the sealed bid first bid auction, where we solicit bids, the winner is the highest bidder, and we charge the winner their bid. The first auction you ever think of is this one. And so on these set of bids, the person who bids 6 wins, and they pay 6. Okay, another auction, which might be the second thing you think of, is the second price auction, where you solicit bids. And again, the winner is the highest bidder. But now instead of charging the winner her bid, we charge her the second highest bid. Okay, so on this example set of bids, the person who bid 6 still wins, but now they pay 4. And so here are the kind of questions that we're going to try to answer with auction theory. So here I've given you 2 auctions. And I might like to know the following thing. Like, if I run one of these auctions, how are people going to behave? So what are the equilibrium of the auction? Okay? And if people are behaving in that way, well, then can I predict the outcome of the auction, like who gets the object? Okay? And if I can do that, well, can I answer the question of which of these auctions is better in terms of maximizing social surplus, meaning giving the object to the person who values it the most, versus maximizing the seller's profit, meaning raising the most amount of money. So let's start with the easier auction to analyze. That's the second price auction, where Again, the winner is the highest bidder, but they pay the second highest bid. And let's try to figure out, if you were a bidder bidding in this auction, how should you bid? So in other words, suppose you have a value for some object I'm selling. Suppose your value is 7, right? What bid are you going to submit into the auction? All right, well, let's think about that. And in particular, let's just suppose we had some extra information. Let's suppose we knew the maximum of the other bids. So let's let T be the maximum of the other bids, and suppose we knew that. Well, now I know what's going to happen in the auction, right? If I bid more than T, then you're going to win, and you're going to pay T. And if you bid less than T, you lose and pay nothing. Right? That's exactly what happens. So if we knew T, we knew exactly what happens. And now we can sort of optimize what's going to happen, what we want to happen based on our value. And there are two interesting cases, right? There's the case where your value is bigger than T, and the case where your value is less than T. And why are these cases interesting? Well, in the case where your value is bigger than T, then if you win and you pay T, you have a positive utility for the outcome, right? V minus T is positive. And in case 2, if you win and pay T, you have a negative utility because V minus T is negative. Okay, so now I can plot, in both these cases, your utility as a function of your bid, which is really easy, because if you bid above T, you win, and you get your value minus T, which in the first case is positive, and in the second case is negative. And if you bid below T, you lose and get utility 0. Right? So these are two cases that we could be in, and your goal is to maximize your utility, which means if we're in case 1, you want to bid above T, and if we're in case 2, you want to bid below T. And there's one particular bid you can make that you don't have to know what T is. That's to bid V, your value, because V is above T in this case, and V is below T in this case. So if I bid my value V, then I maximize my utility, and I don't even have to know what T is. Okay, so in fact, it's your dominant strategy in this auction to bid your value. So what can I conclude about this auction then? So in equilibrium, we should expect people to bid their value, right? And the auction assigns the object to the player with the highest bid. So if bids are values, then it assigns the object to the player with the highest value. So indeed, it maximizes social surplus, right? We do give the object to the player who values it the most. OK, I want to move on to a much more complex problem. Let's take the first price auction. OK, so here the winner is the highest bidder, and you pay your bid if you win. How should you bid in this auction? Again, suppose your value is 7. How are you going to bid in this auction? And what you should realize is that there isn't a dominant strategy like before. It's not going to be quite so easy. Okay? Why is there not a dominant strategy? Well, if you knew the highest of the other bids, and your value was above that, you'd want to bid just sort of epsilon above that highest other bid, right? Because you're paying your bid. So you want to win, but you don't want to win and pay any more than you have to. And so if you knew this highest other bid T, then you would bid accordingly. But you don't. So there isn't a single bid you can put in that's best. Okay? So there's no dominant strategy equilibrium here. And so we're going to have to turn to some more complicated analysis to understand what's going on. Okay? So I'm going to, before doing that, I'm going to have a quick review of some probability. So the uniform distribution on 0, 1 is if I draw V randomly, uniformly from 0, 1. And I'm going to draw my random variables in light blue to denote them as random. And so the cumulative distribution function for this random variable I'll denote by capital F, and that's just the probability. Capital F of Z is just the probability the random variable is less than Z. And the density function is the derivative of that, which is, in this case, for the uniform distribution, just 1. The expectation of a random variable is its integral with its value times the density, and the density is 1 in this case, so it's just 1/2, and pictorially, that's this integral, right? And if I want to integrate some function of my random variable, then it's just the integral of the function times the density. The density is still 1. And so in particular, with the function g I draw in there, it's this area. So I'm going to do everything with mostly pictures today. And so this is what we should be thinking about in pictures when we think about expectation. Okay, and the last thing I want to tell you about uniform random variables is that in expectation, meaning on average, they evenly divide the interval they're over. So if I drew 2 random variables, uniform on 0, 1, then I would expect the highest one to be at 2/3, and I would expect the lowest one to be at 1/3. Okay? Good. So now I'm going to return back to equilibrium analysis. So we have 2 bidders, you and me, let's say, and let's suppose our values are uniform 0, 1. And so my question for you is, how do you want to bid in this auction, this first price auction? Okay, I maybe should tell you a little bit more information. So let's suppose that you knew that I was going to bid half of my value. Okay, so my value is uniform 0, 1. I'm going to bid half my value, which is, so my bid is uniform 0, 1/2. And now you want to figure out what to bid. Well, now this is an easy optimization question, right? Because you know your value, and you can calculate for any bid you put in your utility. So let's do that. Okay, so how should you bid? So you want to calculate your expected utility given your value. And remember, your value to you is not random. You know what your value is. It's 0.7. Okay? And your bid is also not random. You have to put that in. So you want to calculate your utility, which is random because the auction is doing some random thing when it gets my bid, which is random. And what is that? Well, if you win with bid B, right, then you get utility V minus B. Okay, so that is your expected utility if you with bid B minus B. Okay, so what is the probability you win with bid B? Well, that's the probability that my bid is less than your bid, right? And my bid is half my value, right? Okay, so rearranging, that means my value is less than twice your bid. And this is the definition of the cumulative distribution function. And for uniform random variables, it's just the identity, which is just 2b. Okay, so now I have a formula for what your utility is as a function of your bid, which I can optimize by taking its derivative and setting it equal to 0. And I get that it's optimal for you to bid half of your value. So if I'm bidding half of my value, then you want to bid half of your value. And by symmetry, right, if you're bidding half of your value, then I want to bid half of my value. So we're kind of stuck here, bidding half of our value. So that's an equilibrium. Okay, and what can we say about this equilibrium? Who's going to win the auction? Whoever has the higher value is going to win the auction. If we're both bidding half our value, then the person with the higher value wins the auction in equilibrium. So does this auction maximize social surplus? Yes, it does. Okay, I now want to ask a very similar question about profit. We said the two interesting objectives were surplus, social surplus and profit. And we saw two auctions, the second price auction and the first price auction, and they both had the same surplus. They both gave the object to the person with the higher value in equilibrium. Okay, what about profit? So suppose I have, again, two bidders, and their values are uniform 0, 1. Okay, so let's start off with the easy question. What is the profit of the second price auction? Two bidders, values uniform 0, 1. The second price auction, the winner is the highest bidder. They pay the second highest bid. What's our expected profit? All right, let's start thinking about this slowly. So we're going to draw two values from the unit interval, right? Call them v1 and v2. We'll sort them. So v1 is bigger than v2. So player 1 is going to win. And they're going to pay, well, the bid of player 2. But the bid of player 2 is equal to the value of player 2, right? And so what is that? in expectation? 1/3, thank you. Expectation value is evenly divided the interval, and so the profit is the expected value of V2, which is 1/3. Great. What is the expected profit of the first price auction? The same. I had a vote for the same, which is absolutely correct. Why is it correct? Well, here in the first price auction, the player who has the higher value wins, right? And they pay their bid. And what's their bid? Well, it's half their value. So half of the expected value of V1 is just also 1/3, because the expected value of V1 is 2/3. So, well, that's odd. Both the first price auction and the second price auction have the same revenue in equilibrium also. So that's not a coincidence, actually. That is a consequence of one of the most important theorems from economic theory, which is the revenue equivalence theorem, which says that two auctions that have the same outcome in equilibrium, meaning the same person wins, right? And we saw in the first price auction, the second price auction, in both auctions, the player with the higher value wins, so they have the same outcome. Two auctions with the same outcome will always have the same expected revenue. Actually, something slightly stronger is true, which is that if you look at the expected payment a player must make, given their value, suppose your value is 0.7, right? And I say, do you make a higher expected payment in the first price auction in equilibrium or in the second price auction in equilibrium? Well, actually, they're the same in both cases. So actually, your equilibrium payment, given your value, is the exact same number in both the first price auction and the second price auction. And so if I asked you, if you're a bidder with value 0.7, you're like, well, which auction do you prefer, first price or second price? You actually don't care. They're the same to you. Yes, I got a question.
The first one is, that's assuming that you don't have any information or can't do some computation to figure out what the other bidders might, what their value might be, and instead just have to go on these independence assumptions, right? The second question is, you said that you showed an equilibrium for the first price auction. Is that the only equilibrium?
Yeah, okay, so there are two questions. One question is, what if some of the players have extra information about other players' values? And you can do auction theory in that model, but it makes things more complicated, and you're correct, the equilibrium I solved for wouldn't be the right answer. The second question was, are there other equilibria than the one I showed where you bid half your value? And the answer is no, there are not. So that equilibrium is unique, and the only assumption that you need for uniqueness is the IID assumption, the players from the same distribution. I do not need uniform. It doesn't matter what the distribution was. Okay? So because of this consequence, because if I know your value, I know your expected payment regardless of the auction, I'll just have this notation for that payment of V. Okay, so if I'm doing a first price auction or second price auction, I don't care. If I want to know what the payment of the player is with value V, I'll just call that payment of V. Okay, I now want to demystify something that happened a second ago.
Can you give an intuitive explanation of that result? Is there some simple explanation for why it's true?
Of the revenue equivalence result?
Yeah.
So I guess the intuitive explanation is each player is trading off their utility, and the utility is value times probability of winning minus payment. And these are the same trade-offs for both the first price auction and the second price auction. You'd expect that as they trade them off, they kind of balance. Now, so there are two competing properties, right? So in the second price auction, you're going to bid more because you're paying the second highest bid, but not the first highest bid, right? And the first price auction, you bid less because you need to shade your bid down. And these things exactly balance, it turns out. And they're exactly equal. Actually, I think you might get some intuition from this construction, which talks about solving for equilibrium. Okay, so we did something kind of mysterious when I asked what happened in how you should bid in the first price auction, which was I said, suppose I'm bidding half my value. What are you going to do? Okay? And so we started with this kind of miraculous guess that I was bidding half my value when we asked the question what you were going to do. And what if I didn't even know that? How would I have figured that out in the first place? And it's actually really easy using revenue equivalence. So I'm going to show you how to do this for a slightly different auction. So let's change auctions to what's called the Allpay auction. In the Allpay auction, we solicit sealed bids. The person who bids the most wins, and everyone pays their bid. Okay? So for example, on these bids, the person who bids 6 wins, and every single bidder pays exactly their bid. Okay? That's the Allpay auction. Good, I want to solve for equilibrium in this auction, so let's guess, right? What do you think is going to happen in this auction? Who's going to win? Someone with the higher value is going to bid more than anyone else, right? Probably it's going to be a monotone bid function of your value. The more higher your value is, the more you want to bid. That's a good guess, and if the person with the highest value wins, then this is going to be revenue equivalent to the second price auction. Great. So I'm going to solve for equilibrium strategies by writing down 2 equations for what you should be paying. Okay, so on the first hand, in the Allpay auction, your bid is equal to your payment, right? Because you always pay. And remember, payment was our fancy notation for your expected payment in equilibrium given your value. But in the Allpay auction, you always just pay that, right? So these are equal because it's Allpay. Okay, well, the next equation I can get comes from looking at the second price auction. Well, the Allpay auction, if I guessed right that the highest value wins, well, their expected payment is equal to the expected second price payment, which is what? Well, that's the expected second highest value conditioned on winning times the probability you win, right? Because in the second price auction, if you win, you pay the second highest value. Well, and this is really easy to write down, right? So let's take uniform 0, 1. Right? For uniform 0, 1, if my value is v, what's the probability I win? It's v. Good. And what's the expected second highest value given that value v wins? Well, this is the second highest value now, we're conditioning it to be less than v, right? So the second highest value is uniform 0, v. And so that is v over 2. Fantastic. So your bid should be v over 2 times v, or v squared over 2. And that's going to be the equilibrium strategy in this auction. Okay, if we'd done this for the first price auction, we would have gotten the v over 2 instead of v squared over 2. So now that I have some understanding of how people behave in these strategic environments, I'm going to apply that understanding to address this issue in the crowdsourcing contests of, how much work is wasted, et cetera. This is joint work with Shuchi Chawla and her PhD student Balu Savan, who are both at the other UW, Madison. Okay, so a mini overview of the remainder of the talk. I'm going to be relating crowdsourcing contests to Allpay auctions. And that should seem kind of intuitive, right? Because in an Allpay auction, everyone pays. In a crowdsourcing contest, everyone works. And then I'm going to show the loss from wasted work is small, which is great because it means that as a means of procurement, this is a very effective means of procurement. And also it means that I don't have to feel bad about myself for doing this crowdsourcing and wasting a bunch of people's time. And then I'm going to say, well, if we wanted to change the rules of the crowdsourcing contest to get the best rules in terms of maximizing the quality of the work we got for the money we spent, what would the best rules look like? Okay, so let's write down a model for crowdsourcing. So let's normalize our reward to $1. And then let's see, what does contestant I how are they thinking when they face this crowdsourcing contest? Well, they have some skill, which we'll call VI. That's how good they are at working. And they're going to put in some effort, EI. And I'm going to assume that the quality of work they produce is just the product of their skill times their effort. Okay, so the quality is PI equals VI times EI. Good. And when we run the crowdsourcing contest, they either win or they lose. So XI is going to be 0 for lose or 1 for win. And now we can write down what their utility is. The player's utility is, well, how much money they make minus how much work they had to do, their effort. Now, our goal in crowdsourcing, what do we want to do? We want to get the best quality work. What's the quality of work? Well, that's PI equals VI times EI. So we want the best quality, meaning we want to maximize the maximum work of the person who works the most. Okay? That's our goal in crowdsourcing. All right, and let's compare that to the Allpay auction. So in the Allpay auction, I had one item for sale, and what was the bidder thinking? A bidder was thinking, I've got a value VI for the item. I'm going to bid some amount, and my payment is equal to my bid, so I'll just call those the same thing. So PI is your bid, and PI is also your payment. Again, either this player wins or they lose the item, so we'll call XI whether they win or lose. And what's the utility of the player? Well, the utility is their value times whether they win or not minus their payment. Right? And they're always making the payment, so this is the equation for their utility. And of course, if you're trying to maximize revenue, then you want to maximize the sum of the payments. Okay, so good. These look kind of similar, but let's make them look even more similar. So this player is trying to maximize their utility. And from their point of view, their value is a constant, VI. They know their value. It's a constant. I can multiply that by both sides of the equation, and it doesn't change what they're trying to optimize. Right, so let's do that. And then let's note that VI times EI, well, that's just your payment. Right? And so now I see that the thing they're trying to optimize is exactly equal to the thing they were trying to optimize over here. Right? It's VI XI minus PI. So what do we know? Well, we know that so players are trying to optimize the same thing. They have the same equilibrium. Right? So the equilibrium that we solved for a few slides ago is exactly the equilibrium of the crowdsourcing contest. And what's the difference? The difference is, compared to the standard objective, which is profit, we actually care about maximizing this other thing, which is the maximum payment of any player, the person who pays the most. That's what we're trying to maximize. Okay? In other words, the payments made by losers are wasted relative to the two problems. Okay, so I now want to compare crowdsourcing to conventional procurement. So what happens in a crowdsourcing contest? Everyone works. The works of the loser is wasted. It's like an Allpay auction. Okay? What about conventional procurement? Like if the government was going to put out a request for quotes, then they get a bunch of quotes from contractors, and what do? They pick the contractor with the best quote and make that contractor do the work. So that's actually kind of like a first price auction. Okay? And no work is wasted. Okay? So, but actually, the first price auction and the Allpay auction are revenue equivalent, meaning the work done, the total work done in both scenarios is the same. Right? Well, if the total work done in both scenarios is the same, then my loss from doing crowdsourcing relative to procurement is exactly equal to the wasted work, the sum of the payments of all the losers. Okay? So what that means is I had two questions, right? I wanted to compare crowdsourcing to conventional procurement, and I wanted to understand how much work is wasted, and those are actually the same question. Okay, so this is the kind of miraculous result that we're able to show. Essentially, the amount of wasted work is at most a factor of 2 of the total amount of work. And I want to give you some intuition for why we're getting a factor of 2. Because you think of, well, if I have a crowdsourcing auction with like 20 players or 18 players like I had, right? Then why is not the work distributed more evenly across the players? So if I'm wasting a lot of work by throwing out these 17 players who lost, right? Why is that not the case? And it's actually pretty easy to see, right? Look at the payment function. Remember, the payment in equilibrium is the same as the second price payment in equilibrium, which is the expected second highest value given winning times the probability of winning. Okay? And notice that, well, a lot of people probably have a really low probability of winning, which meaning a lot of people are scaling their payment down a lot. And let's take an example. Let's suppose it was uniform 0-1 with 100 players, and your value was a half. What's your probability of winning in this Allpay auction? You have to beat 99 other players, and your value is a half. So your value needs to be higher than 99 other players. And each other player's value is below a half with probably 1/2, right? So this is 2 to the minus 99. So you're taking the expected second highest value, which, I mean, I don't even care what that is, right? It's a number less than 1 because the value is uniform 0-1. And you're scaling it by 2 to the minus 99. You're bidding something super tiny. Okay, so in fact, in the crowdsourcing contest, the qualities of work drop off really, really fast. Okay, and only the strongest and maybe the second strongest player do any real work. And if you remember the examples I showed, there was one great one, and one okay one, and a bunch of ones that weren't even close. Right? So it's kind of, you see that playing out in what I showed. Okay, so what this means is if you're unlikely to win, you have almost zero payment.
Jason, just to be clear, you're saying that the skill levels were uniform, but the efforts put in were dropping off really, really fast.
That's correct.
Which is why
So skills are uniform across 0-1. So the player with value 1/2, who's kind of in the median, he's going to bid a really, really tiny amount. It's not going to be proportional to his value. Yes?
So it seems like this all depends on you knowing what your value is.
Yeah, so there's some dependence. Yeah, the question was, does this depend on you knowing your value? And this depends on knowing your relative strength relative to the other players. Okay, that's what it depends on. And you might think, that's a strong assumption. But actually, if you look at these markets where they're really doing this, these players are playing these same games over and over and over again. There are people who just like go on these crowdsourcing sites and draw graphics all the time, and that's their living.
So tell me if this is a bogus analogy. That this sounds a lot like writing grant proposals. Everybody is putting in the effort, and someone wins.
No.
And
So let me.
I would argue that writing a proposal is not an efficient task. That there's a tremendous amount of work wasted on unsuccessful proposals. By this analogy, it says that everyone just gives up and writes a crappy proposal.
So the question was about the comparison between these Allpay contests and grant writing proposals. And I actually claim they're a little bit different. And the reason why I claim they're a little bit different is because if I wanted to make an analogy to grants, it'd be like the following. First, you do the research. And then, if you've got the best research of everyone, I will give you the money. Okay? So that's really what we're talking about. Now, you can ask the question of how costly is writing the proposal compared to doing the work. And I don't know, I guess usually you write a proposal, it takes maybe a month, and the research you do for that proposal is maybe 2 years, 3 years, 5 years. So hopefully the amount of work you spend on the proposal compared to the amount of work you spend doing the research, it's really small, close to negligible. And therefore, in terms of the equilibrium, that amount of wasted work it's more like a first price auction. Okay? So in fact, it's a mixture between a first price and Allpay, where it's mostly first price and a little bit Allpay. Okay? And so the equilibrium is more like the first price auction. Yeah?
Do we all have to know the value of n, or do we you have to agree on a distribution for the value of n?
Yes, you have to know how many players are involved to calculate your equilibrium strategy, as you can see from the fact that your probability of winning is a function of the number of players, given how strong you are relative to the distribution. And in all of the crowdsourcing contests that are run on the internet, there's a method where you sort of indicate your intention to produce something in that contest, and this is then public. So the number of competitors you expect to have in the contest is actually posted on the contest.
Is that another game?
Excuse me?
Is that another game, registering your intention?
To do theory, you have to ignore some details and hope that they're not relevant. And sure. To actually formalize this argument, is another question, yeah.
Kind of following on the last one, so if you as the person who has started the contest see that there are a lot of players, do you expect to get nothing really very good out of it?
You expect to not get much very good out of all the low players. But remember, if it was a first price auction, having a lot of players is great because they're all competing and it's going to drive the price up. And what I'm saying here, if the loss of wasted work is small, that means I'm getting half of what I would have gotten in the first price auction. So actually, a lot of players is great.
Just because some of them will happen to have higher...
Yes. Because that means the distribution of the max is higher, and we're getting then a higher quality work. Okay, so more players is actually better. It's a great question. Okay, so the actual analysis here is really kind of amazingly easy. So I wanted to walk through it. So I want to show that the winner's expected payment is more than the loser's expected payment. So pick any player who may win and may lose, and let's look at the contribution that they make to the winner's payment and the contribution they make to the loser's payment, and then sum over all players, but that's just 6 multiplying by n. So we don't have to consider that. And I just want to then show that W minus L is positive. So what is W? Expected payment if a player wins, which is their payment times their probability of winning. And L is expected payment if losing, which is the payment times the probability of losing. And so W minus L can be simplified to this simple formula. Okay? Remember from revenue equivalence that your payment is given by this formula. And this formula, let's break it down into a couple pieces. Let's call this thing, this complicated part, G of V. I'm actually not going to care what it is. And this part, well, if it was uniform 0, 1, this is the probability that V beats n minus 1 other draws, which is with probability V each. So that's just V to the n minus 1. Okay? So plugging in this definition of payment into the previous formula, I get that W minus L is this kind of obnoxious looking equation. And again, G of V is some weird function I don't understand. What I'm going to do is I'm going to analyze the expected value of this formula. In fact, I'll plot it first, right? It looks like that, right? And actually, you can see that from this plot that the expected value is positive because the green area is bigger than the red area, right? And G of V, what is that? That's the expected second highest value given your value is V and you win. Well, that's a monotone function of V, right? So what that means is you take this function and multiply by a monotone function, and so you're making bigger values bigger, which only improves the fact that the expectation is at least 0, and so W minus L is positive. So that's really easy. And this kind of analysis is really easy because we started with a really amazing theorem, which is the revenue equivalence theorem. And that kind of theorem makes all kinds of analyses really easy.
So this applies to any IID distribution of...
That's correct. So when I said here I use the uniform distribution for calculating that V, but I could do a change of variables into probability space and get the same thing. That basically this thing is your probability of winning given your strength, which is uniform, and then this is some monotone function of your strength. So a change of variables will make the whole thing work for general distributions. Okay? I now want to talk about the last topic, which is optimizing over crowdsourcing contest rules. So we were talking so far about a very simple crowdsourcing contest rule, which is everyone does some work, the person who wins is the person who does the most work, and we give all the prize to that person who did the most. But there are other crowdsourcing contest rules you could think of. And in fact, the one I mentioned earlier is actually used by TopCoder. So TopCoder is a programming crowdsourcing website. So if you're really good at programming and you want to make some extra money, you can go on TopCoder and get paid to write little programs. And how does TopCoder reward people? Well, if you have $100 for a programming project, then the person who has the best submission is going to get 2/3 of that $100. And the person who has the second best submission gets 1/3 of that $100. And that's how the payoff is made. OK, so, well, is that good? Or was the Tassian method good of giving all the payoff to all the award to the winner? Like, what's the best rule amongst all rules? And in fact, there are two kinds of rules you could imagine. You can imagine static contests where there's a fixed division of the reward amongst the players based on their qualities, right? There's a fixed division, so 2/3, 1/3, 0, 0, 0, right? Or you can imagine dynamic contests which change the division based on the distribution of qualities, right? If I have the best submission just way above everything else, then they get the entire reward. And if their best and second best are close, then I give them 50-50, right? You can imagine a dynamic rule too. So the question I have now is, well, if we get to come up with our own crowdsourcing contest rules, we get to design the mechanism, what is the best mechanism to use? OK, and so here's the result. Among static contests, highest bid wins is the one you want. OK, that means the Tassian rule is better than the TopCoder rule. Always. Always in my model, I mean. And the question about dynamic contests is actually similar. So if we suppose the distribution is nice, and by nice I mean monotone hazard rate, which is satisfied by uniform, normal, exponential, a lot of standard distributions. For instance, distributions that aren't bimodal usually have this monotone hazard rate property. Aren't bimodal, aren't heavy-tailed. Then the best contest is highest bid wins with a reserve on quality. And this is exactly, actually, what the Netflix challenge was. You remember the Netflix challenge from 5 years back, maybe? They said $1 million to the machine learning group that can produce a collaborative filtering algorithm that improves the Netflix suggestion by 10%. What is that 10%? That's a reserve on quality. OK, so this is exactly this kind of mechanism. OK, and so this assumption required monotone hazard rate, and if you want to get rid of that assumption, then you get a characterization of dynamic contests, which says that what you want to do is come up with bins of quality. OK, and you look at, basically you throw the entrants into bins based on their quality, and then amongst the people in the top bin, the highest quality bin that there's anyone in, you pick one of them at random or you divide the prize evenly, it doesn't matter, it's the same thing. Okay, so this is what contests look like. Any questions about that? Those were the three things I wanted to show you. So what did we do here? We took a strategic economic scenario with scarce resources. We analyzed it using auction theory. And in particular, we modeled the crowdsourcing contest as Allpay auctions. Because of nice theoretical results from a couple of Nobel Prize winners in economics about the structure of equilibria in auctions, we're able to really easily analyze and understand what happens in these crowdsourcing contests and show that the loss from wasted work is small, which is great because it means they're effective means of procurement. And we were able to solve for the optimal crowdsourcing mechanisms. We were able to show that over all mechanisms, all perhaps wacky multi-stage mechanisms, and one question I get a lot is, what happens if the contest has several stages and we let people know what the other entrants are in these several stages? Right? Well, when I optimized, actually, I optimized over things that included those kinds of mechanisms. So in fact, you don't want to release any of this information. You want to keep all the information private. and do a highest bid wins or highest bid wins with a reserve price or this bucketing thing.